Hello, this video is about electromagnetic waves. And electromagnetic waves have many regions, including light waves, light X-rays, cosmic rays, gamma rays, ultraviolet, infrared. All of these are electromagnetic radiations. It was James Clerk Maxwell who, even before we realized and recognized that light is an electromagnetic wave, he gave the properties of electromagnetic waves. In fact, we're going to look at Maxwell's 4 equations that form the foundation of the electromagnetic study. And he also connected the speed of electromagnetic waves with the permeability and permittivity of space. We know permeability is a magnetic property, while permittivity is an electric property. So the electric and magnetic properties come together to show that an electromagnetic wave is nothing but an electric wave and a magnetic wave moving perpendicular to each other. Let's see that. Look at this. This is the representation of an electromagnetic wave traveling in one direction, but in real life, the waves travel in all directions. This is just one direction that is shown here. And as you can see, the electric wave shown by the blue vectors is always at right angles to the magnetic wave shown by the the pinkish vectors. And you see that when one becomes maximum, the other also becomes maximum. You see that? So they are, in that respect, in phase with each other. They become maximum and they become minimum at the same exact time. So that's the representation of an electromagnetic wave. And also remember that the electric and the magnetic vectors are always perpendicular, but as it comes towards us, for example, it's continuously rotating in this way. It's continuously rotating. Both are rotating, but they're always at right angles to each other. And they're also traveling in all directions. Before we go any further, we have to recognize the fact that there are 2 kinds of waves. One is the mechanical wave. The other is the electromagnetic wave. Mechanical waves are waves that are formed in the ocean, or the best example may be sound waves. Mechanical waves always require a material for propagation. So they need some kind of matter through which they propagate. And the propagation is because of the vibrations of the material atoms. So if you look at the sun, don't you think that the sun produces a lot of sound? Well, yes, it does. But that sound that is produced by the sun is fortunately not able to reach us, because in space there is miles and miles of emptiness where there is no material. And since there is no material, sound waves that are mechanical waves are not able to pass through. On the other hand, electromagnetic waves can travel through empty space because it's an electric wave and a magnetic wave, and they can go through free space. And since light is an electromagnetic wave, it just comes through, and we are fortunately able to receive both light and heat, plus the ultraviolet, and so on from the sun. So now, having known the difference between these 2 types of waves, let's look at the regions of the electromagnetic spectrum. It's called a spectrum because it's so many wavelengths. And many times there's no clear demarcation between the regions. But as a whole, or approximately, you can say that there are all these regions. And having said that, if you look at this diagram, you see the wavelengths the wavelength is going this way and it's decreasing as you go. From left to right, the wavelength is decreasing. But on the other hand, the frequency is increasing. Yeah, we know that because frequency multiplied by wavelength gives speed, right? Frequency multiplied by wavelength gives speed. And so if you rearrange, wavelength is speed divided by frequency. You see, the frequency is in the denominator. So as one increases, the other decreases. So here are the regions of the electromagnetic spectrum. We'll start from here. You have a broad region called radio waves, broadly, but within that you have also microwaves, because these waves have a little bit smaller wavelength than this part. So the microwaves, the microwave oven uses microwaves, of course. Those waves have a slightly smaller wavelength than waves used for radio broadcasting. And then you have the infrared there. Infrared is nothing but heat rays. So when you say infrared rays, they are nothing but heat rays. And then you have a tiny, tiny region here, which is the only region that we can see with the human eye, and that's called the visible region. That is the visible region. And then on the other side, you have ultraviolet, followed by X-rays. Right now, the frequency is increasing until when we get to gamma rays, the frequency is so high. Remember that the energy of a wave depends on its frequency. Energy is directly proportional to the frequency. So the higher the frequency, the bigger the energy. And that's why gamma rays that have highest frequency also have a lot of energy, and they're able to actually go create mutations, genetic mutations by affecting the chromosomes. So they are that powerful. Gamma rays are dangerous. They have a lot of energy in them. So think about X-rays. They also have a lot of power, and they could be harmful. That's why we do not want anybody to be exposed to a lot of X-rays for a longer time. So now let's look at those regions again. You can also notice that, another thing is, you see, the frequencies just below red are called infrared. See, infrared. And the frequencies just above violet are called ultraviolet. Remember, the word ultra means higher, infra means smaller. So infrared frequency just smaller than that of red. Ultraviolet frequency just more than that of violet. And also, this is just the bandwidth used for AM radio broadcasting. AM stands for amplitude modulation. Amplitude modulation, we'll get there. And this is the bandwidth used for FM radio broadcasting. FM is frequency modulation. So there are two types of modulation. We'll be there in a minute. And this is also used for TV broadcasting. Did you know that in television, both light and sound are broadcast? Oh, of course, everybody knows that. But remember that the picture is amplitude modulated while the sound is frequency modulated. Yes, the picture is amplitude modulated and the sound is frequency modulated. So there are two signals, the sound and the light signal, that are both broadcast at the same time and received by the television receiver. And again, visible region is approximately from, talking about wavelengths, from about 400 nanometer to 750 nanometer. Write that down, 400 nanometer to 750 nanometer. 400 is about the wavelength of violet, and 750 is the wavelength of red. Another important point we have to know at this time is, why do we use red to signal stop or danger? That's because red has a higher wavelength, and therefore it's able to pass through fog and mist and all that. So red light could be seen a long way off, even if it's a misty morning. So that's why red is used to signal stop. So those are the regions of the electromagnetic spectrum. We're going to look at each one of those regions individually and see how they are produced, what their properties are, and especially we will look at their application with respect to life sciences. But before that, why do we call this a spectrum? There should be some common property between them. Yes, all of these are neutral. That means you cannot sway or deflect electromagnetic waves using an electric or magnetic field. That's funny, isn't it? You can't. It'll go straight through. Second thing, and very important, is all of these rays have the same speed, which is 3 times 10 to the power 8 meter per second. To be noted, 3 times 10 to the power 8 meter per second, which is about 300,000 kilometers per second or 186,000 miles in a second. That's how fast electromagnetic waves travel. Here is how the speed of electromagnetic waves is calculated. The formula for speed of electromagnetic waves is related to, just like I told you before, the permeability and the permittivity of free space. And this is the formula. C is 1 by square root mu naught times epsilon naught. We know that mu naught is 4 pi times 10 to the negative 7. Epsilon naught is 8.85 times 10 to the negative 12. When we put those numbers and calculate, we get 3 times 10 to the power 8 meter per second. So that's how you get the speed of light. I also want to talk about the visible region a little bit more here. We'll come back to all those other topics later, but this is what I was talking about. The visible region is highly magnified now, and you can see that infrared is about 750 nanometer. See the nanometer there. And then violet is a little less than 400. I think 385, 386 nanometer. And those are the wavelengths that you have to remember. I just have to say that the eye is most sensitive to bluish green light, which is about the color of trees and plants. Not surprising, is it? That's where the eye is most sensitive to. Next, let us look at how electromagnetic waves were first produced by a German scientist called Heinrich Hertz. You heard that name before because the unit of frequency is Hertz, Hz. So what he did was he used a circuit as shown here, and the circuit, I hope you can recognize the components. There's a resistance, inductance, and a capacitance connected in series to an alternating source of EMF. So that is an LRC circuit that we just looked at. We know that an LRC circuit produces resonance at a particular frequency, which is given by F is equal to 1 by 2 pi square root LC. So in this setup, the circuit produces waves, electromagnetic waves, that are coupled using a transformer. Again, we looked at a transformer. It works using mutual induction. And then those electromagnetic waves are thrown out into space using a gap here. It's just a conductor with a small gap, which actually gives us visual evidence of waves being produced, because we will see sparks, intermittent sparks coming there and making us know or realize that electromagnetic waves are being produced. And so that's how the electromagnetic waves are produced. So it's basically using an LRC circuit with an AC source of energy. And on the other side of the room, Hertz had another loop with a similar gap loop 2, which functioned as the receiver. So you have the transmitting loop here and you have the receiving loop. And across the room, he found that there were sparks that were produced in the gap of loop 2. How exciting that should have been the first time he saw it. So for the first time in history, electromagnetic waves produced by an LRC circuit is traveling through free space and is being received by another loop. This started the idea of radio television transmission. It's that important. So that is how electromagnetic waves are produced. I also want to say that he experimented with this. We know that the formula for velocity is the product of frequency and wavelength. So what he did is he found out the frequencies, he calculated the frequencies, and that's how we recognize that these are nothing but light waves, that these have exactly the same speed as light waves. From there, as research continued, we found that there are other regions that also have the same speed. The easiest way to understand the production of electromagnetic waves is by considering a straight antenna connected to an AC source. So that's like a long rod or straight conductor, connected to an AC source. At time t is equal to 0, when we start, you can see that the charges are maximum separated. That means the electric field is maximum at that instant, separating the charges, because you know that positive charges tend to move in the direction of the electric field while the negative charges go away from the electric field. So that separates them to a maximum because the electric field is maximum. So that's what you see there. And then, so if you look at this picture, it's clearer. A quarter of a cycle later, you see that the charges have come very close. The negative and the positive have come very close. So the electric field is 0. And then another quarter of a cycle later, we see that, look at this diagram, we see that the charges have now crossed. So it started with negative here, positive here, then they approached, and then now they've gone to opposite sides. So now you have the positive at the top and the negative at the bottom. So again, the electric field is maximum, but in the opposite direction compared to before. So that's why we have this maximum of the electric field, which is now in the negative direction. And then this process continues. So as the charges move back and forth, the electric field moves accordingly. But also remember, according to Ampere's rule, a changing electric field will also give rise to a magnetic field. A changing magnetic field. So a changing electric field now gives rise to a changing magnetic field. As you can see from these diagrams, you know that around a straight conductor, the magnetic field is in what? Concentric circles as given by the right-hand rule. Okay, so you have a changing magnetic field also there. So now you have both an electric field which is changing and a magnetic field that's also changing, which is represented in this way. And that is essentially how electromagnetic waves are produced and propagated. An important thing that we have to remember is that although the electric and magnetic fields are continuously changing, there is a connection, there is a relation between them. At any particular instant, if you take the magnitude of the electric field and divide it by the magnitude of the magnetic field, so if you take the ratio E by B, guess what? You are going to get the speed of light. So that's a very important result. Though electric and magnetic fields are changing, at any particular instant, this ratio E by B is always a constant and is equal to the speed of electromagnetic waves. So now for a minute, let's look at antennas. When we talk about an antenna, did you know that inside a microwave oven, there is a tiny antenna that's connected to an AC source, and it's that antenna that's producing those microwaves that actually cook your food. So there is a tiny antenna there. And if we look at receiving antennas, for example, here, this is a typical receiving antenna that you don't find usually nowadays. This antenna has different elements, metal rods that have varying lengths, because the length determines the wavelength that is being received. So it says it has cross wires of various lengths to most efficiently receive different wavelengths. Nowadays we don't use this. We receive television either using cable, or we use a dish, not as big as this. This one has it's a diameter of 50 feet. So no, we use much smaller ones. And this dish, for example, shown here, is both a transmitter and a receiver. It's able to transmit and receive. On the other hand, the direct TV or dish TV dishes that we have are just receivers. Remember that at the focus of those receivers, you actually, the focus of the dish, you actually have a a receiver that, when it receives, it's a very weak electromagnetic wave that has to be amplified several times before it can produce the sound and the light that we watch and listen to. So there's a lot of amplification going on there. All right, we'll look at that soon. So here is a very important part of this chapter. Here is a table that's presented. The table talks about the types of waves, how these waves are produced, the application of these waves, the application, and also the applications with respect to life sciences. And then we also talk about the issues with these waves. Anything that's useful also has harmful effects, okay? So I'm not going to read out all of this, but I'm going to talk about it generally so you have an idea. So when we talk about the production of these, we generally see that the lower energy waves, which is radio waves, radio and television broadcasting waves, they are produced by accelerating charges. Okay, so because they are of lower energy. But as you come down, the energy increases, and you see that thermal agitation comes in. And then infrared waves are produced by thermal agitations and electronic transitions. What do you mean by electronic transitions? When the electrons go from a higher orbit to a lower orbit, they lose energy, and that's the energy that comes out as infrared, visible light, ultraviolet. But when we come to X-rays, it's again due to electronic transitions, but this time it's due to transitions in the inner orbits. That means it's like jumping from the second orbit to the first orbit instead of the fifth to the fourth. You see, you get that difference? And in the innermost orbits, the difference in energy is much bigger, which means when X-rays are produced, they are more energetic than ultraviolet, for example. But then finally, when we come to gamma rays, look at it. Gamma rays are produced by nuclear decay. So the nuclear has different energy states. So when the nucleus goes from a higher energy state to a lower energy state, it gives out the difference, and that's what we see as gamma rays. So that's basically how they are produced. Then applications, you can read that, you would understand what it is, especially look at the life sciences aspect of that. You see that radio and television waves are also used for MRI. And then you have what's called deep heating, where you can heat inside, heat the tissue. Look at all that. And then, we need ultraviolet rays to a certain extent to produce vitamin D. And then X-rays and gamma rays are used for cancer, therapy. To a certain extent, it's successful. That's what we call radiation treatment. That's what we use. But all of these have harmful effects. And issues are primarily with X-rays and gamma rays that funny enough, they can be used to heal cancer, but they also cause cancer. And then when you get to ultraviolet rays, we know that it causes the depletion of the ozone layer that produces, that brings in the ultraviolet light and causes a lot of harm. I'm going to show you a picture where you see how much of the ozone layer has been depleted. And the greenhouse effect is caused by infrared rays. Remember that when you grow plants in glass houses, what happens is most of the energy passes through the glass, and after it passes through the glass, its wavelength decreases. So they're not able to go back out because the wavelength is decreased, and so they stay inside and thereby increasing the temperature. That's what is called the greenhouse effect. That's also caused in the atmosphere, but that's how the name came about. All right, interesting. Microwaves are also used for cell phone transmission and so on. So look at this table, look at that generally, and this chapter in the textbook gives you a detail of all of these, and which you should read and need not memorize, but just look at the important facts that's given there. Thank you. Let's talk about another aspect of radio and television broadcasting, which is called modulation. Okay, so the thing is, let's imagine that somebody is speaking through a microphone and the sound waves are converted by the microphone into electrical signals. But these electrical signals are of very small amplitude. That means they have very less energy content in it. So the power or the energy of these waves are not enough for them to be directly broadcast, because they won't even go about maybe 10 meters, 5 meters, and that's of no use. So this content that is to be broadcast is called a signal. So here it's an audio signal. So this is somebody saying, you see that? So that's the audio signal that is to be broadcast, but like I said, it doesn't have enough energy to be broadcast on its own. So what is done is this audio signal is now mixed with what's called a carrier wave, which has a higher frequency. Okay, so this carrier wave, this one, has a higher frequency. As you can see, the wavelength is very small, which means the frequency is really high. And energy depends on frequency. You remember that? So this wave has a lot of energy in it. So now, if the required audio signal could be mixed with the carrier in some way, then it would go a long way off because of the energy in the carrier. Now, this process of mixing can be done chiefly in 3 ways: amplitude modulation, frequency modulation, and phase modulation, which is not even mentioned in your text. So anyway, in amplitude modulation, what is important is to understand that the amplitude of the carrier is changed according to the amplitude of the signal. So the resulting wave that you get, or the amplitude modulated wave that we get, is as shown here. Look at that. You see that the amplitude has changed. So like this one is a constant amplitude carrier, but now the amplitude of the carrier has been changed according to the amplitude of what? The signal. That's why it's called amplitude modulation. Again, the amplitude of the carrier is changed according to the amplitude of the signal. That's why it's called amplitude modulation. And in fact, both of these halves are symmetric, and in radio transmission, it's only half of this that is usually transmitted. Okay, so that's amplitude modulation. Now, what about frequency modulation? There's one important difference. The frequency of the carrier is changed according to the amplitude of the signal. Let me show you that. So that is the carrier again. That is the audio signal. And now look at it. This carrier had a constant frequency, didn't it? Has a constant wavelength, that means constant frequency. But now, where the amplitude of the signal is maximum, look at it. Where it's maximum, the frequency is maximum. See that? Where the amplitude of the audio is minimum, like negative, so minimum, the frequency of the carrier is the lowest. So that means the frequency of the carrier has been changed according to the amplitude of the signal. That's why it's called frequency modulation. So the important points are given here. These are the two types of modulations that you have to know. You have to be able to recognize them, draw diagrams, and look at the differences between the two. Well, now we have to take a look at Maxwell's equations. So, since it involves a lot of calculus, you don't have to actually write the equations. You only need to know the basis of getting these equations. What Maxwell actually did is he combined 4 laws that we already know, that we have studied in this semester. He collected them. Let's look at them. Number 1, we know that electric field lines start from a positive charge and end on a negative charge. Remember? They start from positive and end on a negative charge. So that is the first one. And we know that the permittivity of free space is involved in drawing those field lines. And this is actually, it could be called the Gauss's law for electricity. Gauss's law for electricity. So that's number 1. Number 2, when we look at the magnetic lines of force, what do we know? We know that the magnetic lines of force go from a north pole to a south pole, but don't end there. They go back from the south to the north. So if you have a bar magnet, it goes from the north to the south and goes back to the north. So magnetic lines are closed loops. Okay, they are closed. So what goes out comes back in. And this is the Gauss's law of magnetism. So that is Maxwell's second law. The third law is where we talked about a changing magnetic field produces an electromotive force, an EMF. Do you remember that? A changing magnetic field produces an EMF. What was that law called? It was called Faraday's law of electromagnetic induction. And there we also studied Lenz's law that gives the direction of that EMF. So combining Faraday's law and Lenz's law, we get Maxwell's third equation. And finally, to get the fourth equation, we look at what's called Ampere's law. I hope you remember Ampere's law. Ampere's law talks about B is equal, calculus, B is equal to mu naught times I, where you talk about all I can say is, just for you, without the calculus, I was struggling to explain it, but here it is. Magnetic fields are produced by moving charges or by changing electric fields. Okay, that's all. So in Faraday's law, we saw that changing magnetic fields produce electric fields. In Ampere's law, we see that changing electric fields produce magnetic fields. Just flip them. So those are 4 Maxwell's equations. Again, we're not writing the equations, but I've just given you the fundamentals of how he wrote down those equations, and I hope it makes sense. To conclude this chapter, let's look at the average intensity of a wave. You remember that intensity is defined as power passing through 1 meter squared. Intensity of a wave is the power passing through unit area or through 1 meter squared. And intensity of a wave always depends on the square of the amplitude. So if the amplitude is doubled, the intensity quadruples. So intensity is proportional to the square of the amplitude. So you don't have the math to derive these formulas. So you just need to have an idea of these without actually deriving these equations. So here's the first one. So that's I average. Average intensity is given by C epsilon naught E naught squared by 2. Now what are the terms? C is the speed of electromagnetic waves. Epsilon naught is 8.85 times 10 to the negative 12. E naught is the maximum value of the electric field. So we can calculate the average intensity in an electromagnetic wave using that formula. But by substitutions, we can also get this formula. And we are basically substituting using C is equal to E by B. I'm writing that there. And epsilon naught is 1 by mu naught C squared. Okay, I've told you both of these before. So we are basically making two substitutions and getting this relation from this one. Should be able to figure out how we get that. Okay, so it's C B naught squared by 2 mu naught. So the interesting thing is this is a formula in terms of the maximum electric field. This is the formula in terms of maximum magnetic field. So depending on what is given, you'll have to use one of these equations. But there is a third and very interesting equation that we can get by remembering that C is also E naught by B naught. C is E naught by B naught. Or E naught is C times B naught. That's what's coming up. So you take C B naught, replace it by E naught, and then you have another B naught, and then you get this. This formula has both electric and magnetic values. So there are three equations. The first one only in terms of the electric field, second in terms of the magnetic field, and the third one in terms of both the electric and magnetic fields. And you get one from the other. So these are the three formulas that you'll have to use when you're asked to calculate the average intensity of an electromagnetic wave. Well, in closing this chapter, I also want to talk about demodulation. It's the opposite process of modulation. So in a receiver, remember you have amplitude modulation and frequency modulation in a receiver. But when in a transmitter, in a transmitter you have those. In a receiver, when you get that wave, remember that wave, the required audio is mixed with a carrier. The carrier has served its purpose when it reaches the receiver. So once it reaches the receiver, we got to separate the two again. Separate the carrier from the audio and then continue with the audio because we only need the audio. That process of separating the carrier from the audio is called demodulation. So there is modulation and there is demodulation. This chapter is really a very important, a big chapter, but for you, devoid of the mathematics, it's just chunks and pieces that have been given, and that itself is of crucial importance for you in your higher studies. So look at the textbook and read more about each part of the electromagnetic wave, because surely you'll be tested on that in the exam. Thank you, and see you on the next video.